Introduction: Designing and developing a smart mobility board with directional control using the PIC18F4580 microcontroller offer an enriching and practical learning experience in the field of embedded system. This project blends hardware components such as switch, LED, DC motor, and a motor driver with microcontroller programming to create an intelligent, responsive robotic vehicle capable of controller, movement, and visual signaling. It serves as an ideal platform to explore the fundamentals of electronic, embedded software, circuit design, and logical problem solving. At the heart of this project lies the PIC18F4580 microcontroller, a powerful and versatile chip that acts as the central processing unit of the system. It is programmed to interpret input signal from switch and execute commands that control output devices like motor and LED. Through careful planning and coding, the microcontroller orchestrates the board behavior, enabling it to move forward, reverse, and make directional turns depending on user input. This functionality simulates basic autonomous vehicle operation, making the system a miniature prototype for real-world application in mobility and automation. The project emphasizes the importance of interaction between hardware and software. DC motor enables the board to move in various directions with the help of the L293D motor driver, which provides the required current and voltage to drive the motor. Switch serves as the primary control input, allowing user to trigger directional movements manually. LED act as visual indicator of the board current state, such as moving forward, turning, or reversing, enhancing both user experience and system debugging capabilities. Additionally, this mini-project introduced students to real-time programming concept and embedded system integration using MPLAB X IDE for code development and Proteus software for circuit simulation. It demands a solid grasp of digital logic, programming skill in C, and an understanding of electronic components and their behavior within a circuit. From circuit design to firmware development, students must plan, simulate, test, and troubleshoot, mirroring the life cycle of real-world engineering projects. Ultimately, the Smart Mobility Board project is more than a technical exercise. It is a holistic journey through engineering design and innovation. It fosters critical thinking, promotes hands-on learning, and encourages creativity in problem solving. It not only prepares students for future challenges in the field of electronics and robotics, but also inspires confidence in design and building functional systems from scratch. Objective of this mini project is first, to design and construct a smart mobility board. The primary goal is to create a compact, fully operational robotic system. It involves selecting suitable components, planning the architecture, and building a functional board that can be controlled through program logic. This process builds a strong foundation in embedded system design. Second, to implement and refine directional control. A key objective is to develop effective control machine for the board movement, whether through manual switch or automatic sequence. The system will demonstrate the ability to move forward, reverse, and make directional turns, allowing the user to understand motor control and logical flow in real time. Number 3 is to evaluate system performance through testing. Iterative testing is essential to validate the board response to input. Through trials and refinements, the project aims to ensure smooth operation, correct signaling via LED, and effective motor condition. This evaluation guides improvement and ensures user interaction and system reliability.
Let's begin with the input and output components used in this project. There are a total of 4 input components which are 4 push-button switch. This switch allows the user to control the movement of the motors in different directions. On the output side, we have 4 leads that serve as indicators, 2 DC motors to provide movement, and 1 motor driver IC, specifically the L293D, to interface between the microcontroller and the motors.
Next, we move on to the program coding. A brief explanation for the program code is that the program is written in embedded C for the PIC 18F4580 microcontroller. First, the configuration bits are set to disable the watchdog timer and enable high-speed oscillator mode. The main function begins by setting port B as input for switches and port C as output for the motor, controller, and LED indicators. Now let's move on to the mini project observation, where in figure 2.0 the LED green is turned on. This is because when no switch is pressed, the green LED turns on and both DC motors will stay idle. This indicates that the system is in idle mode or stop, which means that there will be no movement. In figure 2.1, the LED blue is turned on. This is because when switch 1 is pressed, the blue LED will turn on, and in this state, motor M1 and M2 will rotate at a normal speed in a clockwise direction. This configuration shows that switch 1 is used for turning the boat to forward direction. Figure 2.2 shows that the yellow LED is turned on. This is because when the switch 2 is pressed, the yellow LED starts blinking, and in this state, motor, which is M1, rotates at a normal speed in a clockwise direction, while motor M2 stays in idle mode. This indicates that the systems shows that the switch 2 is for turning right. And in figure 2.3, as you can see, the yellow LED is turned on again, which means that the switch 3 is pressed. When switch 3 is pressed, the yellow LED starts blinking, and in this state, motor M1 will stay in idle mode, while motor M2 rotates at a normal speed in a clockwise direction. This configuration shows that the switch 3 is used for turning left. And lastly, which is figure 2.4, as you can see that the LED red is turning on. This is because when switch 4 is pressed, the red LED turn on and both motors M1 and M2 will rotate anti-clockwise. The result will indicate that the system is in a reverse operational mode, which causes it to go in the opposite or reverse direction.
Now, I would like to share the cost estimation of the project. The main controller, the PIC 18F4580, costs 35 ringgit. The 4 LEDs cost a total of 6 ringgit 48 cents. The L293D motor driver is 8 ringgit 90 cents. 2 DC motor costs 12 ringgit. The power supplies or battery costs 6 ringgit and the 4 switch costs 2 ringgit. Altogether, the total cost of the project is 70 ringgit 38 cents, which is quite affordable for a functional mini project.
The benefit of the project: the development of a smart mobility board with directional control using the PIC 18F45X0 microcontroller offers numerous educational and practical benefits in the domain of embedded system and robotics. This project helps students understand the fundamental interaction between hardware and software, especially in time-real systems where input from switch are processed to control output like LED, fans, and motors. By simulating movement functions such as forward, reverse, and directional turns, learners gain hand-on experience in motor control and embedded programming using C in MPLAB X IDE. The use of the Proteus simulation also provides a risk-free environment for circuit testing and debugging, reinforcing the concept of system validation. Furthermore, the integration of visual indicators (LED) enhances user interaction and provides immediate feedback, improving both usability and troubleshooting efficiency. The simplicity and scalability of the design make it suitable for foundational education in embedded systems while laying the groundwork for more advanced automation for robotic projects. Ultimately, the project cultivates critical thinking, creativity, and confidence in designing functional, real-world electronic systems from scratch. In conclusion, the Smart Mobility Boot project successfully integrates the core principles of embedded system design, motor control, and interactive system evaluation. The design and construction phase laid a solid technical foundation, emphasizing component selection and system architecture. Directional control implementation showcase real-time motor coordination and logical discussion making, enhancing understanding of embedded control system. Finally, system testing and refinements ensure reliable performance, accurate input response, and effective LED signaling. Altogether, the project not only meets its objective, but also strengthens practical skills in microcontroller-based development and autonomous system operation.